Where should we look to see the Voyager spacecraft? Could we turn craters on the moon into giant radar dishes? And is the best kind of artificial gravity constant acceleration? All this and more in this week's question show. Welcome to the question show. Your questions, my answers. Now, as always, wherever you are across my channel, if a question pops in your brain, just write it down and I will gather them up and answer them here. Now, we record this show live every Monday at 5 p.m. Pacific time. So if you want to have your question answered live, like as soon as you think of it, I will answer it, as well as have follow-on conversations and conversations with the rest of the audience. You should definitely come and join the show. We do this every Monday at 5 p.m. Pacific time. Now, before we get into this week's question show, I want to bring you back to the book club. And this, of course, was a way for you to recommend books to me, and I will read them, and then I will tell you what I thought. And so I was able to go all the way through the Revelation Space series. I read Project Hail Mary. There's a bunch of other books that I read. And so the most recent book that had been recommended to me as part of the book club was a book called Accelerando by Charles Stross. And this was recommended to me by a bunch of people, both from the sort of space flight, science fiction side, but as well as the artificial intelligence singularity side. And it is the craziest book I think I've ever read. It starts out, and the book is about 10 years old. And so when you're reading the book, it's projecting forward into the future about a decade, which is like now. And so you're reading it, you're going, oh, you missed all these things. The things that you thought were going to happen didn't happen. But then the book jumps every 3, 4, 5 years at a time, sort of playing through the life of a family as they approach the singularity. And it's the first book that I've ever read that really properly understands what exponential growth feels like. And so even though you're 20, 30, 40 years into what's happening, the scale of things are just going off the charts. Like 50, 60 years into this, they've dismantled Mercury, Venus. They have, people are copying themselves into computers. They're sending those computers on missions to other star systems. They are resurrecting dead people. Like it goes on and on and on. And yet there's also a really interesting story that goes along with it. So that's Accelerando, Charles Stross. I highly recommend it, but you've got to pay attention because it is dense. So the book club, I'm reading books you're recommending. So go ahead. There's going to be a link down in the show notes, but essentially there's a Goodreads group where you're just making book recommendations. I'm picking them based on what sounds interesting to me. I'm reading the book and I'm letting you know what I thought, and then you can follow on as well. So please, I need another book. Let me know what to read next. Mike Sully 7212. Which way do we look to see where the Voyager spacecraft are heading? Like, I want to point at them. Yeah, the Voyager spacecraft were launched in 1977 and have been traveling in space for like 45 years. And they're definitely running down in their power, but they're not out of power yet. And so they're still sending transmissions home. And like they are in space and they are in constellations. And so NASA has to turn these gigantic dishes in the sky towards the location of where the Voyagers are if they want to be able to send and receive signals from them. So Voyager 1 is currently in the constellation of Ophiuchus, and it's moving towards the Little Dipper. And so like 50,000 years from now, the closest star that it will come to is located in the Little Dipper. So if you know where Ophiuchus is, you can point your telescope and like you can look up the exact right ascension declination location for the Voyager spacecraft. You won't see anything, of course, because they're so far away. Even the most powerful telescopes on Earth couldn't see them. But if you had a really big radio dish, you could receive their transmissions. Voyager 2 is in the constellation of Pavo. And same thing. You can point your telescope and you can actually see where the spacecraft are. But yeah, they are out there in space in constellations that you might already know. You might have noticed the planet name that's popped up over my shoulder, and that's a way for you to vote to tell us which of the questions you thought was the best. And last week, the winner was Tatooine. I guess the kind of snarky comment about how I can describe scientific discoveries with a straight face. And so congratulations, Stephanie McGuire. You asked the best question, or maybe I gave the best answer. Whatever, we work as a great team. So thank you for everyone who voted last week. And remember, if you want to help me know what questions you like, what you want to see more, clearly you want me to give an enthusiastic response about the scientific method for snarky trolling questions. So I guess that's just all the show will be from here on out. Anyway, go ahead. You'll see the planet names above my shoulder, the end of the show. Vote for the one you like the best. Just write the name of the planet in the comments down below, as well as part of your question or whatever, and we will tally them up and we will celebrate that here next week. Herner Weisenberg 7052. Are there roughly parabolic shaped craters on the moon that could be turned into giant radar dishes with minimal effort by coating them with radar reflective material? One of the cool things about the craters on the moon is that they are almost all roughly circular and parabolic shaped. And it seems weird, doesn't it, that you would assume that the rocks that are crashing into the moon are coming at all of these different angles, and yet the craters all look like nice circles that are scooped out in this very similar way. And what happens is that whenever any object strikes the moon or the Earth or whatever, it's going so fast, like it's going, in many cases, kilometers a second, tens of kilometers a second. They can be going very fast. And when they strike their target, then all of the kinetic energy is instantly pushed into or released onto the planet that they hit. And so even though an object can be coming in at a very steep angle, as soon as it really smashes into the moon, all that kinetic energy is released straight into the moon and creates this giant crater. And they look quite circular. And you're exactly right that they would be the perfect place for a telescope. The problem is that they're not smooth enough. They're very smooth, but it's not quite what you need. You would need to sort of get in there and polish up these craters on the moon to actually turn them into a proper telescope. But there's been some great ideas. And in fact, I did an interview here on the channel that what you do instead is you set up pylons on sort of around a crater of whatever size that you want. And then you extend a net down from those pylons so that it is hanging down into the crater, and it's going to be following this parabolic shape thanks to the lunar gravity. And then that great big radar dish can be a monster radio telescope that could be, say, a kilometer across. You could make other kinds of telescopes, but then the tolerances are going to get harder to get it to. So radio is very forgiving. And so the wavelengths are very long. It's okay if you have a not perfect telescope, but once you get down to infrared, visible light, then you do need to have something that's a little more carefully machined. But I do really like this idea that you use these craters on the moon as natural sort of telescope lenses for building your telescopes. Vernon Goins. There is no such thing as artificial gravity. The only way to mimic gravity is by constant acceleration in space. Please give up on the big wheel in space. It won't work. So according to Einstein, if you're in a box, if you're in a room and you're sitting on a chair and that box is down on the surface of the Earth, or that box is in a rocket that is constantly accelerating at 1 g of gravity, or that box is on the inside wall of a gigantic space station, say thousands of kilometers across, that is rotating, you wouldn't be able to tell the difference on which one you are. They would all feel equivalent to you. That is general relativity. Now, according to your question or your comment, the only way to mimic gravity is by a constant acceleration in space. Obviously, that would be the best, right? You take some rocket that gives you 1 g of acceleration and you fire it for days, weeks, months, years, and everybody on board your spacecraft has 1 g of gravity. They just go about their business. They walk up and down stairs. They can have baths. They don't suffer muscle loss, bone loss, vision problems, fluid redistribution. Everything is the best. That just sounds wonderful. The problem is that we have no way to produce 1 g of constant acceleration. Our rockets, our chemical rockets, can produce 1 g of acceleration for minutes at the most. We don't have ion drives that can produce constant acceleration for any length of time. We don't have the technology. Even nuclear rockets wouldn't be able to provide 1G of acceleration for long periods of time. We don't know how to make fusion drives, and maybe even those wouldn't be able to provide you with the 1G of acceleration that you need for long periods of time. And what if you want to just stay in one spot? What if you just want to be in orbit around a planet? You don't want to hop on your sci-fi drive expanse spaceship and fly off. Like, are you just going to fly off to the far side of the solar system and then fly back and forth to give everybody 1G in their space station? Like, no. So you're going to need some kind of artificial gravity in space. And the way that we know is going to work is a giant rotating wheel. Now, obviously, the engineering challenges of building a giant rotating wheel are ludicrous. Like, we have trouble launching more than a few tons into orbit at a time. And when you think about some of the O'Neill cylinders, some of the really like giant mega projects, like you're looking at thousands of tons, millions of tons. And so in the short term, it's going to be really tough for us to be able to do that. The most practical form of artificial gravity that we're probably going to be using in the next couple of decades is the variety that tries to mitigate some of the health problems that astronauts will experience when they're in space. So you're not going to have this beautiful, giant, rotating space station where everybody is sitting around and you look up and you can see the top of the space station and there's everybody's homes directly above you and you're stuck to the outside of the station. It's going to be that you're living in a space station like the International Space Station. You're in weightlessness most of the time. And then there's a centrifuge that you go and maybe you sleep in the centrifuge, or maybe you put in a couple of hours in the centrifuge every day. And all it's trying to do is help minimize the amount of damage that your body is taking because you are in space. So it's like saying, like, obviously going on ships is a bad way to get from continent to continent. What we need are stargates. Teleportation is the way to go. Like, we don't have the technology. And so until we have the technology to provide constant 1G acceleration, we're going to have to use the stuff that we know how to use. And then we'll wait. And then if someone provides a 1G accelerating drive, then everything changes. And being able to use that for artificial gravity is like the least of the benefits of having access to a 1G constant accelerating space drive. Bakhtir Jawuk: is stopping at the gravitational focal point for gravitational lensing a problem at high speeds required to get a telescope that far? How do they decelerate, or does it not matter? So you're talking about the solar gravitational lens, which is one of my favorite ideas. And I've had a chance to interview Dr. Slava Turishev about the solar gravitational lens. I just did another interview with Slava Turishev about the method of propulsion that he thinks will be able to get out to the solar gravitational lens, as well as go to other really interesting places in the outer solar system. So if you haven't checked out that interview, this is me telling you to check it out. Like, just look at the comments on that interview and how excited people are about what we talked about in the interview. I highly recommend it. He's definitely got some pretty big ideas, and we get into the weeds on that. So the idea of the solar gravitational lens, this is that at about 650 astronomical units away from the sun, the gravity of the sun acts as a natural telescope lens. And so if you put a telescope at that focal point, you can then magnify the power of your telescope by many orders of magnitude. And for example, it could give us an image of an extrasolar planet at a 1 megapixel resolution. So you could see another Earth at 1 megapixel resolution as opposed to a single pixel, which would be wonderful. And so the question you're asking is, like, once you get out to the solar gravitational lens, you're going to keep going, right? If you've had to go tens of astronomical units every year, you're going very fast. And so then once you pass that 650 astronomical units, you just keep going. How do you stay in the focal point? Well, the cool thing about this is that you can remain in the focal point. That once you cross that 650-ish astronomical unit range, then it's this cone of focus. And as long as you stay in that cone for the entire time, you can continue to make observations using the sun. In fact, it gets better and better over time because the sun gets smaller, stops being such a big glare in the focal image that you're producing. And so you don't have to worry. You don't have to stop. You just turn back and you just keep drifting for tens, hundreds of years, and you can keep using the gravitational lens as long as you want. Arg Scott, is there a benefit to making larger helicopters for future Mars missions? So at the time that we're recording this, NASA's Mars Ingenuity helicopter has flown over 51 times. Like, they were expecting just to get 5 flights out of the helicopter, and now they're up to 51. And it's been so successful. Like, imagine like what life was like for videographers before they got drones, right? They had to like shoot images from street level, and now they can have these great sweeping shots as they're on their skateboards around New York City. It's game changer. And so it's kind of the same on Mars. You've got this helicopter that's flying around and is able to observe the route that the rover is taking from above. And geologists just have a field day when they can do this, because then they can see the larger structures, things they want to go and examine. And this was just a test, like, does a helicopter work on Mars? And the answer is yes. And so the next big question that scientists are going to need to ask is, how much science, how much geology, how much exploration can a helicopter do on Mars? And my guess is a lot. That any and every future mission that's going to go to Mars is going to come with a helicopter sidekick of varying sizes. In fact, right now they're planning to send a helicopter with the Mars sample return mission. If there's any problem with the main samples that are on board Perseverance right now, like when it delivers the samples to the Mars sample return mission, then they can go and fly out and pick up the backup samples. These are the ones that Perseverance set down on the surface of Mars. And the helicopter will have a little grabber arm. So it'll fly out along the route that Perseverance took. It'll pick up samples, bring them back to the Mars sample return mission, and then be able to return those back to Earth. There's something just so amazing. Like, it feels like it was impossible. And now suddenly you've got this entirely different axis of flight, right? You had X, Y, and now you've got Z, and it's great. And in fact, it's been so successful, the Chinese are planning to put a helicopter in one of their upcoming rover missions. And I think it would be unthinkable to not add a helicopter to every single mission that ever goes to Mars. And you can imagine when the astronauts go to Mars, they're going to bring helicopters with them. They're going to deploy them all around for all kinds of purposes, where to go explore the next day, as scouts, as helping figure out some of the dangers that they face. Now, the question you're asking is there any benefit to making them larger? And the answer is, I don't think we really know what are the limits. I mean, the rotor on the helicopter is turning very quickly, and it's got this sort of perfect balance between the size of the rotors, the mass of the helicopter, and the amount of power that it's able to bring in from the sun. And if you make a much bigger helicopter, you're going to have to play with those variables. And so the thing's going to be heavier. Maybe the rotors won't be able to spin as quickly. And you might find that, in fact, like, you're constrained in engineering. So the one thing I can guarantee is that we will see every possible variation of helicopters in future missions. If you like my answers to your questions, as well as the other things that we do at Universe Today, consider joining our Patreon club. This allows us to keep minimum ads for everyone. Like, as you can see, there are no ads during this video. As a patron, you'll also get an ad-free experience on universetoday.com for life, even if you unsubscribe. You'll get ad-free videos, early access to interviews, as well as other perks that are exclusive to our Patreon community. Thanks to everyone who's already subscribed, and welcome to the recent newcomers: Joseph Conrath, Patrick Yingst, Richard Hensley, Tim, Scotty Mack, Mary M. Leal, Ty Gardner, Don Byrne, Bruce Berry, and Joseph Gentile. Join the club at patreon.com/universetoday. Rage Quit Quick. What are your thoughts on smart telescopes like Unistellar and Vespera? So I've had a chance to play with one of the smart telescopes, the Vaonis Stellina, and it's amazing. Like, you take this, it looks like a turret out of a Portal game, and you put this thing on the ground and you sync it with your phone, and then you tell it to start, and it figures out where it is because it has a GPS on board, and then it plate solves a couple of images of the sky and then figures out like where it's pointing. It knows what time it is. You then just tell it things you want it to look at. And so you say, well, I'd like to look at this constellation. I'd like to look at that nebula, this galaxy. And then it just goes and finds them and images them. And anybody who's ever owned a telescope knows how difficult it is to polar align the telescope, to be able to sort of show your friends interesting objects in the telescope with very little setup time. Like it is a pain to make a telescope with its go-to setting, like go from object to object. Like once you've got it set up, once it's polar aligned, then yeah, you can go and go like, let's look at M33, let's look at M31, no problem. But you can spend 3 hours going, just a second, while you're trying to get your telescope set up, and it is embarrassing. So when you use these telescopes, like, and I haven't used the unistellar one, but you know, we've done reviews on Universe Today. It's amazing. And it absolutely feels like the future. Like you are using this telescope, you're not having to think about it. It's just pointing it at whatever objects you want to be able to see that are available in the night sky. So the downsides of them are that you're kind of locked into the gear. So it comes with the size of the telescope that it has. It comes with the kind of camera that it has, the hardware that goes along with it. And, you know, we've seen technology increase in leaps and bounds. And so I personally prefer to be able to have all these parts be separate. And so you can swap out the mount with a new mount. You can swap out the telescope lenses or the camera or the controller or whatever as the new technology moves along. They're also very expensive. I mean, you were looking at thousands of dollars. And if you were to go and set up your own astrophotography rig for the same price, you could get a more powerful telescope that is more customizable, that's more modular, but not easier to use. And it really feels like right now there is this gigantic gap in the marketplace that all telescopes should be as easy to use as the ones from Unistellar and Vaonis. Like, it's embarrassing how difficult it is to use a telescope that isn't one of those two. And so, you know, they always say like the best camera is the one that you've got with you, right? And so like the best telescope is the one that you're going to use. And so if you do invest in one of those telescopes, you're going to use it. But you will also run up against its limitations. And so you will, if you use it a lot, you'll realize that the pictures aren't as good as the pictures that you could be taking with a more custom built piece of kit. And so you may then end up wanting to sell the thing and put together your own custom hardware. But like whatever gets you into the field, whatever gets you into the hobby. And so if you're the kind of person who wants to be able to just like see nebulae, see galaxies, see clusters, see the planets, the moon, and not think too much about it, and you're not trying to take like astrophotos that you're going to sell or try and submit to Astrophoto of the Day, they're pretty great. Moonwalker. When the ISS is finally decommissioned, how will they do it? Will they dismantle it and let each individual module fall, or fall all at once? Or are they worried about something might survive re-entry? Right, so the plan right now is that the International Space Station will be deorbited at some point in the late 2020s. Although, you know, we've heard predictions for when they're going to finally deorbit it, and people keep showing up to extend the lifespan of the space station. So at one point the Russians said they were going to pull out of the station. The Americans have said that they're not going to maintain it beyond a certain point, and then a couple of years later they've extended it. And so where we are right now is that it will probably be deorbited at the end of the 2020s. I wouldn't be surprised if it stretches into the 2030s, but like at this point it is a machine and it is running down and it's getting more and more expensive to maintain it. And NASA has budget that it needs to spend on things like the Lunar Gateway, the Artemis missions, other exploration. So it is definitely going to have a hard time limit in the end. And the plan right now is that they're going to deorbit it using sort of three things. There's thrusters on board the station itself, so they're going to be able to fire those thrusters. There are the spacecraft that are attached to it, and they're going to be able to fire those. And that's probably not enough to give it the kind of control that they want. And so the plan is probably to launch some kind of tug. Now maybe it'll be like a beefed up upper stage from that they might use for some other mission, and they'll dock that onto the space station, and that will assist to deorbit it exactly where they want it to go. Where they want it to go is they want the whole thing to crash into the middle of the Pacific Ocean, where they crash most spacecraft when they still maintain control of them. That's where Mir went. That's what many other spacecraft have gone. It's like the farthest point away from any other human being. It's the place that you can crash your spacecraft and do a minimum amount of damage to anybody. And so it'll all just come down together in one big deorbit maneuver, with the station firing its thrusters, with the attached spacecraft firing the thrusters, and this tug to help out as well. Dev Gaikwad, is it possible to make artificial gravity by not using the wheel design like in Stowaway? Yeah, so if you watch the movie Stowaway, they have this spacecraft that flies into space, and then it extends out these modules, and then it starts to tumble end over end. And you get artificial gravity on the two ends of the station. I think they had a counterweight, and then they have their actual habitation module. And yeah, in theory, that method will work quite well. You know, you do get artificial gravity in your module. You probably don't want to go to one full Earth gravity. You probably want to have it spinning like enough so that when you pour liquids, they stay in their bowls, things like that. What I like about that methodology is that you don't need to have the rest of the wheel. Like, you just are spinning this thing end over end over end. You have to be careful about how you structure it, because there are various forces. There's ways that objects that are rotating in space want to orient themselves. And there's a really great video, and hopefully Chad will be able to find it, where an astronaut on board the International Space Station is spinning this handle, and the handle is sort of spinning, and then suddenly it flips over in the other way, and it spins, then it flips over the other way. And so there are axes of rotation that you have to keep in mind. People always worry, like, what happens if the tethers break? But actually, it's not that big of a problem. Like, you are, like, the velocity that you're going towards Mars or wherever your destination is, that's the big velocity. And even if you know, your tether snaps, it's only a slight change between the velocity of the one part of it and the other part of it. And it's probably within your capability, if you have additional fuel on board, to be able to correct and be able to have both parts arrive at the destination as planned. So, I wouldn't be surprised if, when we have long-term space flight, like a mission to Mars, some version of that sort of rotating masses will be supplied to provide gravity to the crew. Waleed Damouni, isn't it easier to do robotic tests on Mars rather than have another mission to bring samples and all that complexity? No, I don't think so. You can definitely do very simple exploration on Mars. Like, you can take a picture of a rock, you can try to understand the chemistry of the rock, you can drill into a rock to sort of reveal a little bit what's underneath. There are various instruments that you can deploy. But when you think about the kinds of labs that we have here on Earth, I mean, a geologist can go into this lab and they've got access to kilns and lasers and mass spectrometers and tools to measure the gas composition. They've got microscopes, electron scanning microscopes. Like, the list of tools they have at their disposal just goes on and on and on, as well as the ability to bring new experiments into play when you think of them, and as they get invented. One thing that's really kind of interesting is that when the Apollo samples were brought back from the moon, they put a bunch of them away in a really secure storage, knowing that the devices to run experiments on would improve over time. And so that when you had this next round of equipment that they could do their tests with, they could bring the samples out of cold storage and they wouldn't have interacted with the Earth's atmosphere at all, and they could do these experiments. And this is ongoing. And so a lot of the times we see new experiments being run on samples from the moon. And so the same thing will happen with Mars, that you'll have these samples brought back from Mars in pristine condition. They'll be put into this place where they won't be influenced by life on Earth, there won't be any contamination of Earth into the samples. And then they'll bring out little bits of the samples and share them among researchers. and then over the coming decades, be able to perform new experiments. And there's just no way that you could replicate at the same level of sensitivity that you can with the Mars Sample Return mission. Like, if there is life in these samples, or if there is fossilized life, or is there any evidence of life, you really do need a lab on Earth to gather the evidence. And like, what you don't want is, you don't want your results to be inconclusive. Like, when you think about how people still argue over what was found by the Viking landers, is because for all of its ability, Viking was a mediocre scientific laboratory compared to what you have on Earth. And so it maybe found evidence of life on Mars, and maybe it didn't. And Mars researchers might still get into heated arguments about what it found and didn't find. And like, that's not helping, right? Like, did you find life on Mars? Maybe, right? No, let's get a really solid answer. And that's why we want to have the samples brought back to Earth, where the best scientists on Earth and the best equipment can try to get to the bottom of this question. Not done. Who decides what person or persons can mentally sit in a tin can for 2 years to get to Mars and be there when there's no blue sky or green trees or anything but rocks and dust? I mean, there are people at NASA and the European Space Agency and the Chinese Space Agency who are choosing their astronauts. And the kind of psychology that they're going to be looking for, the kind of people to be able to handle that length of a mission, they're going to be looking for very special people, people who have demonstrated that they can handle stressful situations very well, that they are experienced with some level of being alone or in a very small group working with other people, maybe people who are part of a submarine crew or have been on some of these missions before. But a lot of the times, like when you fly to the International Space Station or when you go to the moon on the Artemis mission, you will be experiencing challenges, and it's those kinds of stressful situations that will bring out the best in people, or the worst. And so all of the people who are involved in NASA right now, in the European Space Agency, Chinese Space Agency, Russian Space Agency, right, they are going to be under scrutiny from the people saying, like, does this person have the right capability? That also said, I mean, there is a lot of work that's being done in the psychology of astronauts. I actually did an interview with a researcher who has been looking into this and trying to sort of make predictions about what it's going to take to be able to help astronauts deal with the homesickness, the loneliness, the stresses of being far away from Earth, away from easy assistance. It's going to be hard, but we've had human beings who've set out on sea voyages. There are people who solo sail around the world, who serve in submarines. There was a woman who just spent more than a year in a cave by herself. She came out fine. So can human beings handle the solitude and stresses of a mission to Mars? Is definitely something you want to keep an eye on, but I think it is a problem that is relatively straightforward for us to solve compared to the lack of gravity, the constant cosmic radiation, and then all of the things that can go wrong on a multi-year mission to Mars when you're too far away from help. All right, those are all the questions that we had this week. Thank you, everyone, for asking your questions in the YouTube comments, as well as showing up live during the show. Remember, we do this show live every Monday at 5 p.m. Pacific time. And don't forget to vote to celebrate whichever question you thought was the best. We'll see you next week. If you want to stay on top of all the important space news, join my weekly email newsletter. I send it out every Friday to more than 60,000 people. I write every word, there are no ads, and it's absolutely free. Subscribe at university.com/newsletter. You can also subscribe to the Universe Today podcast. There you can find an audio version of all of our news, interviews, and Q&As, as well as exclusive content. Subscribe at university.com/podcast or search for Universe Today on Apple Podcasts, Spotify, or wherever you get your podcasts. A huge thanks to everyone who supports us on Patreon and helps us stay independent and keeps ads at a bare minimum. Thanks to all the interplanetary researchers, the interstellar adventurers, and the galaxy wanderers. And a special thanks to Paul Davis, Vlad Shipolin, Jay Dennis, David Giltonen, Maud So, George, Jeremy Mattern, Jordan Young, Tim Whalen, Dave Verabioff, Andrew M. Gross, and Josh Schultz, who support us at the Master of the Universe level. All your support means the universe to us.